Right, so the last couple of papers have been really clean, like one particular idea, and this is going to be just a jumble of different ideas glued together. So I'm not really going to go into the theory that much. I'm interested in this paper because I'm interested in learning causal relationships, and there's this big unsolved question in causal inference, causal discovery really, when normally a causal discovery system where you're trying to learn what causes what, you start with tabular data. You have observations in the rows and features in the columns. So the question is, where do the features come from? What happens if you just have visual data? And there's not a huge amount of research on this. So this is one of the few papers. It came out just in October last year. So it's a really interesting area. And really hard. So the where you would start if you only had visual data is by interacting with the world. So this paper mixes together causal discovery and reinforcement learning and representation learning. So there's a lot going on. So when would you need this tool that they're developing? Let's say you have a robot butler that needs to learn how to turn on the light switches to make the house light up the way it wants the house to light up. And it needs to be able to do this in lots of different houses because houses are not all wired up the same. And you don't want to have to give the robot butler a wiring diagram of each house. It should be able to figure it out just by flipping switches and seeing what happens. That's the goal. Interact with the world, see what changes, learn how that house is wired up. This is a hard problem even for humans. That's why we have this sign in our office. Sometimes switches depend on each other in ways you don't expect.
Lizzie, you need to add a causal diagram under that.
Yeah. That would be cheating. Okay, so the first step in this process is that you learn how to learn a causal structure of an arbitrary house, because at test time you're going to be given a novel house with a novel causal structure. So we're learning the causal induction model, that's F in this diagram, and the training data is going to be a set of different training environments. Each one of them has a different causal structure. You get to interact with that environment up to horizon H. And for each one of those training environments, you're going to output a predicted causal structure. Yeah, there we go. Second step is take that predicted causal structure and learn a policy for how you would interact with the house, flip the switches to achieve whatever your goal is. You want to turn the kitchen light on, first turn the meeting room light on, and then turn the kitchen light on. And then the last part of the paper is evaluation. So we're going to evaluate this agent, as I said, with a totally new causal structure. It gets to interact with the environment for a while. It tries a bunch of switches, and then it has to achieve some goal. I'm not going to talk about step 2 that much because I'm not the reinforcement learning expert, that is Chris. I'm going to talk more about the causal induction model. So you get images. You get a top-down view of the entire house in the setup that they have in this paper. You are God, you're looking down on the house and seeing which rooms light up when you flip switches. So you can see here that from step 1 to step 2, you took an action and this table lit up. So the first thing you do is pass the observations into this observation encoder to get this encoded version of this image. And then you take the diff between those encoded representations of the state. So you're seeing what changed when you took that action, and that residual plus your action is passed into this transition encoder and edge encoder, and that is going to update the causal model. The the causal model you start out with is a bipartite graph where the nodes on the left are your actions. Those are given, you know what you can act on, but the nodes on the right, the yellow ones, these are the features, these are the effects that you're trying to influence. And those are not given as like columns, they're not given as a particular vector. You have to learn that in your encoder. You have to learn what the features are that you're having an effect on from the images. That's the cool part. So you're getting a representation of the effects of your actions that fits into a causal model. Right. My speaker notes seem to come from the next slide. I don't know what's going on. Oh well. So let's see. Oh, no, my speaker notes. I should have been clicking through that. Right. Pardon me. Yeah, so you get an edge update at each step, delta E, and they also use an attention vector in the transition encoder to see which of those edges the edge update should be applied to. And after each action, you update the weights. So you take your current causal graph and you add this thing, which is the edge update and the multiplied by the attention vector up to horizon H. Now, the interesting thing about this is they have a supervised loss in this learning phase. So they give the model as its reward each time it learns a new environment. What was the true causal environment? Well, they don't give it to the model. That's how they figure out how well the model's doing. The difference between the true causal model of that house, how that house was wired up, and what the model learned. So the only way this works as a training method is if you can train your model in this kind of environment where you have a whole lot of like true houses to train on, where you know how they're wired up. It would not work if you were trying to just unleash the robot on the world and see if it figured out how the world worked. You have to know what the true causal structure is for a set of different training environments. Question?
Graphs we're using are pretty simple.
Yeah.
They account for the...
There are 4 kinds of causal structure that they consider. Pretty simple ones. Let me just go back so I don't forget if there's anything else I'm supposed to do. So there's not an end-to-end reinforcement learning method. You have to have true knowledge of the causal structure to train it. And these true causal structures come from these 4 types. One-to-one, where each action has one effect. One-to-many, where one action can have multiple effects, but you don't have multiple actions influencing the same effects like you do in many-to-one. And then the last case is master switch, where you have a hierarchical structure. There's one switch where once it's flipped, all of the other switches can work, but before it's flipped, none of them will work. So it's a pretty restricted set of causal structures. The effects don't influence each other. Everything that you care about learning the causal effect of is something that you can influence yourself. So these are structures that in the tabular data case would be trivial to learn with causal discovery because you can influence the world, right? But in this case, because you're also learning the representation of what those effects even are, there's this additional layer of complexity, although the fact that it's supervised learning and you know what the true causal structure is when you're training, that really helps with that. And so, yeah.
Is the number of potential output states known in advance?
Yeah, the number of potential output states in their setup, they assume to be the same as the number of actions. Yeah, and they do have to set that as a parameter because this edge decoder has to output a parameter of a certain length. Now, it's okay if there are some extra output states that are just not used for anything. That doesn't hurt. So they could always just set that number higher. That doesn't bother me so much. Right. So they start out in an exploration phase where the agent is just flipping switches and seeing what happens. And they use a heuristic for that. For the first three cases, one-to-one, one-to-many, and many-to-one, the agent just flips each switch once. And then it's out of the exploration phase and has to be able to achieve its goals. In the master switch case, they allow the agent to flip all the switches until they see something happen, and then it can flip all the switches once. And for these causal structures, that exploration phase is sufficient to figure out the structure. If they had a broader variety of causal structures, it would not be enough. But these kind of limitations, I think, would be something you could generalize fairly simply.
Is that scales with depth? The number of sort of actions that you have to do in your.
Yeah, exactly. And if you have some kind of feedback, it's, or confounding, it might not be sufficient no matter what you did. So you're gonna take all that and learn a policy. I won't say too much about the policy learning phase because I'm not a reinforcement learning person, but I will point out a couple of things. Firstly, your goal state is an image. So they figure out how to get to the goal by taking the difference between the current image state and the goal image state. So it's sort of like, what do you want the world to look like? Secondly, the policy takes that causal graph that you've just learned using your causal induction module as an input. So what do you want the world to look like, and how is the world wired up? Those are the inputs. And as the training data for the policy learning, they have the actions of an optimal planner given that causal graph. Don't press me too much on that point. I've got a funny look. Okay, so results. They have some comparison methods. I have no idea where they found these comparison methods because there's hardly any work in this area. But their one is the dark blue one on the right, and it works better than all the others. So yeah, so surprising. So this is the F1 score on learning the causal structure. So basically, if there's no edge in the true structure and you put an edge in, you get penalized. If there is an edge in the true causal structure and you do not have an edge there, you get penalized. And it turns out it gets harder if the problem's bigger. If you have 7 switches, everything is harder. And it is easier if at training time you looked at more different causal structures. They didn't try more interaction with the environment, but having looked at more different types of structures, you do better. So this is 10 versus 50 versus 100 versus 500, 10, 50, 100 different causal structures in training.
Got like different structures in the graphs.
Yeah, exactly. They sample the causal structure when they're setting up the environment.
So when they lost, that's like different housewife.
Exactly, yeah.
With the question of master switch, they create scenarios where like not everything is wired up to that master switch.
I've forgotten that detail.
That's okay.
I read it a few months ago.
That would be interesting how it would have figured that out. It would have just completely broke.
Like multi-causal structures. Yeah.
Yeah, I'm not sure. And the second question is, how well does it do at achieving its goals, getting the house to light up the right way? So the dotted line on the top is how an oracle would do if it were just given the correct causal structure. And you're still learning the policy, so the oracle's not perfect. It only is an oracle for causation. But yeah, if you've seen a lot of causal structures, this method, this is the dark blue one, does better than everything else. Yeah, so, so is that a question? No? Cool. All right. I think this is very cool. Like, there's not much stuff that's trying to figure out how the world works just by interacting with it. It does have some limitations, though, some of which I think you could generalize. So firstly, you have to do supervised training of that causal induction module. Now, there might be a way to do this end-to-end just with reinforcement learning, but I'm not clear on how that would work. Tricky thing to figure out. Bit easier to generalize is the fact that all of the actions have to have immediate effects because they rely on the difference between, you know, one image and the next to see what the effect was. They have to be able to see the whole house at once, full observability, and they can intervene on anything that they want to learn the causal effect of. So I think all of that could be generalized, and it's exciting to see if anyone will do it. And that is all.